Hi, I'm Patrick Reagan, and welcome to Network Switches Part 3, Managed Switch Advanced Features. In this video, we'll dig into specific functionality that you will only find on managed switches. Topics include link aggregation, spanning tree, jumble frames, switch security features, VLANs and routing between VLANs, and Native and Voice VLAN. As always, stick around for the practice questions at the end to test your knowledge and help you prepare for the Network Plus exam. If you find this video helpful, don't forget to click the like button. And if you have not already subscribed, hit that subscribe button and join the Pat Has Your Back community for more tech training content and networking know-how. As mentioned in the last video, managed switches are used predominantly in enterprise networks, where managed switches provide extensive control over configuration, monitoring, and optimization. Key features include Simple Network Management Protocol, or SNMP, which enables centralized performance monitoring and remote configuration. Network admins can track port usage, bandwidth trends, and receive alerts when thresholds are exceeded, helping with troubleshooting and performance tuning. Quality of Service, or QoS, prioritizes critical traffic like voice and video to ensure smooth performance even during congestion. Redundancy via Spanning Tree Protocol, or STP, prevents network loops and ensures continuous operations by dynamically rerouting traffic if a link fails. Virtual LAN, or VLAN support, segregates network traffic for improved security and efficiency. Managed switches can span VLANs across multiple devices using 802.1q trunking. Port mirroring sends a copy of network traffic to a designated port for packet analysis or intrusion detection. Layer 2 and Layer 3 managed switches may be assigned an IP address if you want to manage the switches remotely. Layer 3 switches will also need an IP address to perform routing. While I covered speed and duplexing in the last video, I'm covering it again to complete the specific Network Plus objective. When configuring switch ports, you want to pay attention to a few key settings. Speed, where options typically include 10 megabits per second, 100 megabits per second, 1 gigabits per second, or 10 gigabits per second, depending on the switch and connected device capabilities. Duplex mode chooses between half duplex, where data flows one way at a time, or full duplex, which has simultaneously send and receive. Most modern switches and network devices support auto negotiation, allowing them to automatically agree on the best speed and duplex settings. However, in some environments, especially for performance tuning or troubleshooting, manual configuration might be necessary. Just remember, both ends of the link must match. If one side is manually set and the other is set to auto, it can lead to a mismatch and cause performance issues or even link failures. The maximum transmission unit, or MTU, defines the largest size in bytes of a packet or frame that can be transmitted across a network without fragmentation. MTU values vary by network type and protocol, but in Ether networks, the standard MTU is 1500 bytes. If a packet exceeds the MTU of a given network segment, it must be fragmented, where it's broken into smaller packets. This introduces overhead, as each fragment requires its own headers, and all fragments must arrive intact to reconstruct the original data. Losing even a single fragment results in the loss of the entire packet. Why MTU matters? Because larger MTUs reduce header overhead and increase throughput by allowing more data per packet. Consistency, where MTU settings must align across all devices on a network path to prevent performance issues and fragmentation. Reliability is inconsistency or mismatched MTUs can cause packet loss and degraded performance. Path MTU discovery, or PMTUD, is a technique used to determine the optimum MTU between two endpoints, adjusting packet size to avoid fragmentation along the route. A jumble frame is an Ethernet frame with a payload significantly larger than the standard MTU of 1500 bytes, which is typically up to 9000 bytes, though the exact limit can vary based on the network hardware and configuration. By sending more data in each frame, jumbo packets reduce the number of frames required for large transmissions. This lowers protocol overhead from headers and acknowledgements, resulting in higher throughput for bulk data transfers, reduced CPU usage on network devices, and improved efficiency in bandwidth-intensive environments. Jumbo frames are especially beneficial in settings like data centers, storage area networks or SANs, and high-performance computing clusters where large data sets need to be moved quickly and reliably. Link aggregation is a networking technique that combines multiple physical connections into one logical link. This approach boosts bandwidth, adds redundancy, and strengthens overall network reliability. Key benefits include increased bandwidth where multiple physical links are merged to support higher data transfer rates than a single link could provide. Redundancy and resilience: if one link in the group fails, traffic seamlessly continues across the remaining links, minimizing downtime. Load balancing: where the network traffic is distributed across the aggregated links, reducing congestion and making more efficient use of available bandwidth. And simplified management: so to the network layer, the group of physical links appears as a single connection, streamlining configuration and maintenance. Link aggregations could have two 1 gigabit links combined to create a single logical 2 gigabit link. If you have 4 1 gigabit links, you could form a single logical 4 gigabit link. Link Aggregation Control Protocol, or LACP, is a protocol defined in the IEEE 802.3 AD standard that allows multiple physical Ethernet links to be combined into a single logical connection known as a Link Aggregation Group, or LAG. It operates at the data link layer, Layer 2, where LACP coordinates the automatic formation and maintenance of these groups between network devices like switches, routers, or servers. Key features include dynamic link management, where LACP automatically detects link failures and adjusts the lag accordingly, helping maintain seamless connectivity. Load balancing, where it enables balanced distribution of traffic across the active links in a group. Improved bandwidth and redundancy: by bundling links, LACP boosts total throughput and provides fault tolerance. And negotiation, where it can negotiate which links to actively include, using modes like active and passive to control participation and link aggregation. When connecting switches, it's common to build in redundant paths to ensure network reliability. However, if not carefully managed, these redundant connections can create switching loops. Loops can trigger broadcast storms, overwhelm bandwidth, and lead to denial of service or DOS conditions or severe performance issues. Here's how it happens. When a switch receives a frame with an unknown MAC address, it floods that frame out all available ports except the one it came from. If a loop exists, this frame circles endlessly between switches, multiplying along the way. Eventually, the network becomes flooded with duplicate packets, consuming resources and bringing traffic to a crawl or a complete halt. The Spanning Tree Protocol, or STP, is designed to eliminate loops in Ethernet networks by creating a loop-free logical topology. Operating at Layer 2 of the OSI model, the data link layer, STP plays a critical role in maintaining network stability and preventing outages caused by switching loops. STP uses bridge protocol data units to allow switches to exchange information about their ports in the network topology. Through this process, a root bridge is elected based on the lowest bridge ID, which is a combination of priority and MAC address. The root bridge serves as essential reference points for all STP calculations. Each switch then determines the most efficient path to the root bridge by calculating path costs based primarily on the speed of its interfaces. Lower cost indicates more preferred optimum routes. Benefits of Spanning Tree Protocol include prevents network loops with stopping broadcast storms and reducing congestions that could cripple performance. Enables redundancy, allowing alternate paths for traffic to boost reliability and fault tolerance. And ensures resiliency, automatically recalculating paths to keep the network connected if a link or switch goes down. Each switch in a network designates one of its ports as the root port, the port with the best path to the root bridge. All other ports are placed in specific STP states to prevent loops and ensure a stable topology. Blocking prevents loops by not forwarding traffic. Listening prepares to participate in STP, pairing the MAC table but not forwarding traffic. Learning builds the MAC address table but still doesn't forward traffic. Forwarding, where it's fully operational, forwards data and updates the MAC table. And disabled, where it's manually shut down by the administrator and not participating in STP. If the link fails or a new switch is introduced, STP automatically recalculates the topology and reconfigures ports to maintain a loop-free connected network. The original spanning tree protocol, defined in IEEE 802.1d, provided foundational loop preventions for Ethernet networks. While it offered a stable network topology, its convergence time, typically between 30 and 50 seconds, was relatively slow by today's standards. Rapid Spanning Tree Protocol, or RSTP, as defined in IEEE 802.1w, is an enhanced version of the classic STP. RSTP introduces faster convergence by transitioning ports to the forwarding state within a few seconds. It also refines port roles and states, discarding, learning, and forwarding to streamline network reconfiguration. RSTP is widely adopted due to its speed and backward compatibility with legacy STP. Multiple Spanning Tree Protocol, or MSTP, as defined in IEEE 802.1s, expands on RSTP by supporting multiple spanning trees within a single network. This allows for traffic load balancing across VLANs and improved scalability, especially valuable in large enterprise environments. Managed switches can offer various security features. Port security limits or restricts what devices can connect to a switch. VLAN security includes measures taken to protect a network segmented by virtual local area networks, or VLANs, from unauthorized access and malicious activity. Network access control is a security framework that regulates and monitors device and user access to a network based on predefined policies that ensure only authorized and compliant devices and users can connect to and interact with the network resources. Traffic protection and filtering, which uses access control list, or ACLs, and firewall filters to filter traffic based on various criteria. Layer 2 attack protection, were mechanisms that protect against various attacks, including MAC flooding and VLAN hopping. Of course, don't forget to change the default passwords, and when connecting to a switch so that you can manage it, make sure you're using an encrypted communication mechanism such as SSH so that the password and commands are encrypted and are not seen over the wire. Port security is a layer 2 security feature that allows you to control access to individual switch ports by restricting which MAC addresses are allowed to communicate through them. It helps prevent unauthorized devices from connecting to the network and mitigates attacks like MAC flooding. It also controls the flow of data in and out of the network. Key features of switch port security include a static MAC binding, where admins can manually define which MAC addresses are allowed on a port. MAC address limiting, which limits the number of MAC addresses that can be learned on a port. Sticky MAC addresses allows the switch to dynamically learn MAC addresses and save them in a running config. Violation modes defines what happens when a security violation occurs. Protect drops traffic from unknown MACs and does not log or disable the port. Restrict drops traffic and logs the violation and increases the violation counter. And shut down disables the port in error disabled state, which requires manual or automatic recovery. For example, imagine a corporate environment where only company-issued laptops should connect to the network. With switch port security, you configure each port to only accept a specific number of MAC addresses. For example, 1. If someone plugs another device into the specific port, will automatically be denied without having to specify individual MAC addresses. Optionally, use sticky MAC to learn and remember the device's MAC. If someone plugs into an unauthorized device, the port either blocks it or shuts down based on the violation mode. A virtual local area network, or VLAN, is a logical grouping of devices that appear to be on the same local network, even though they're physically located on different segments. Rather than relying on physical connections, VLAN separate devices logically, grouping them within the same broadcast domain. By segmenting a single physical network into multiple isolated logical networks, VLANs improve security, optimize traffic management, and enhance network flexibility. Devices can be dynamically assigned to VLANs based on port, MAC address, or user authentication credentials. The abstraction also simplifies network reconfiguration, allowing administrators to reshape network layouts without rewiring or relocating hardware. By default, all switch ports reside in the same broadcast domain, so any broadcast frame is sent out through every port regardless of the intended destination. This can flood the network with unnecessary traffic and degrade performance. Virtual LANs solve this by segmenting the switch into multiple broadcast domains. Each VLAN isolates traffic, meaning broadcast frames stay within the assigned group. This not only reduces congestion, but also improves overall network efficiency and scalability. VLAN security benefits include isolation and policy enforcement. Isolation. VLAN segments network traffic, keeping devices in separate broadcast domains. This limits access between segments and reduces the risk of unauthorized communication. Policy enforcement. VLANs help enforce security policies by restricting communications to only authorized devices within the same VLAN. This creates virtual walls that protect sensitive data and critical systems. VLANs also offer traffic management. Enhanced QoS, where VLANs enable more effective quality of service configurations, allowing a critical traffic like voice and video to be prioritized over less time-sensitive data. Traffic segregation, which by separating different traffic types such as data, voice, and management, VLANs streamline traffic flow and optimize bandwidth usage. This reduces congestion and improves overall network performance. IEEE 802.1q, or VLAN tagging and trunking, is the standard that defines how VLAN tagging and trunking work in Ethernet networks. VLAN trunking has a communication link, usually Ethernet or fiber, that carries multiple signals or VLANs simultaneously. Trunks are used to connect switches or network segments, providing network access between 2 points. Think of it like the trunk of a tree, carrying data to and from many branches. This allowed network segmentation without requiring separate cables for each VLAN. VLAN tagging, where each Ethernet frame is tagged with a 4-byte header that identifies the VLAN to which it belongs. This tag contains a VLAN ID, or VID, which enables switches to correctly handle and route traffic across VLANs. In 802.1q VLANs, an access port is configured to belong to a single VLAN, and it removes the VLAN tag before forwarding frames to end devices like PCs or printers. Access ports are typically used to connect end-user devices. An access port can carry traffic for only one VLAN, called the access VLAN. When packets get delivered to the end device, such as PC or printer, it does not tag the Ethernet frames with a VLAN ID. In fact, it removes VLAN tags from incoming frames before delivering them to end devices like PCs or printers. Essentially, the end device does not know about VLAN, and as far as the end device is concerned, it just connects to the network and sends and receives packets. The VLAN ID is used to get to the packets to the correct VLAN before being delivered to the end device. Dynamic Trunking Protocol, or DDP, is a Cisco proprietary protocol designed to simplify the management of trunk links between switches. It automatically negotiates trunking on a link, allowing Cisco switches to dynamically establish trunk connections without manual configuration. This makes VLAN management more efficient, especially in large or evolving network environments. The native VLAN is the default VLAN assigned to a trunk port for handling untagged traffic. When a frame arrives at a trunk port without a VLAN tag, it's automatically assumed to belong to the native VLAN. By default, many switches use VLAN 1 as the native VLAN. However, for security best practices, it's recommended to assign a different VLAN to reduce the risk of VLAN hopping and other potential exploits. A VLAN database is a storage area on a network switch, typically a layer 2 or layer 3, where information about configured VLANs is stored. It maintains a list of VLANs and their associated parameters such as VLAN ID, VLAN name, and sometimes additional metadata depending on the platform. It ensures VLAN persists after reboots, supports VLAN consistently across trunk links and VDP domains, and prevents accidental VLAN loss if running config isn't saved. On Cisco switches using VDP, which is known as VLAN Trunking Protocol, the VLAN database is saved in a file called VLAN.dat in the flash memory. To enable communications between VLANs, you need a device capable of layer 3 routing, typically a router or a layer 3 switch. Another common method is using Switch Virtual Interface, or SVI, which is a logical layer 3 interface configured on a switch. An SVI provides IP connectivity to a specific VLAN and serves as the default gateway for devices within that VLAN. By configuring SVIs for each VLAN, the switch can route traffic between them internally, eliminating the need for external routers and enhancing performance. This setup enables efficient inter-VLAN routing, allowing devices on different VLANs to seamlessly exchange data through the switch. Private VLANs, or PVLANs, are an advanced feature used primarily in large layer 2 network environments to provide additional segmentation and security within a single VLAN. PVLANs enable more granular control over traffic between devices, allowing better isolation and reducing the risk of unnecessary traffic exchange between hosts. The private VLAN always has one primary VLAN. Within the primary VLAN, you'll find the promiscuous port, although the ports can communicate with the promiscuous port. Within the primary VLAN, you'll encounter one or more secondary VLANs. There are two types: community VLAN, where all ports within the community VLAN can communicate with each other, and the promiscuous port. Isolated VLANs, where all ports within the isolated VLAN are unable to communicate with each other, but they can communicate with the promiscuous port. Use cases for private VLANs include: PVLANs are widely used in data centers to isolate tenants or servers from each other while allowing controlled access to shared resources. Service providers use PVLANs to isolate customer traffic while still allowing access to shared services like DHCP or internet gateways, and creating isolated security zones within an enterprise network to protect sensitive data or systems from unauthorized access. For example, imagine a network with PVLAN 1, which is an isolated VLAN for guest devices. PVLAN 2 is a community VLAN for employees. Guests will still connect to the promiscuous port, which will allow internet access, but are not allowing access to each other. Employee devices on PVLAN 2 would be able to connect to each other and to the internet. A voice VLAN, also known as an auxiliary VLAN, is a specialized VLAN dedicated to handling voice traffic such as voice over IP or VoIP calls. It prioritizes voice packets over other types of data to ensure smooth call quality, minimizing delays, jitter, and packet loss. Voice VLANs isolate VoIP traffic from regular data traffic, preventing voice streams from being disrupted by broadcast or congestion on the data VLAN. This separation improves performance and ensures that time-sensitive voice communications isn't compromised. In typical deployments like corporate offices, a PC is connected to a VoIP phone, which in turn connects to a switch. The IP phone is assigned to a voice VLAN, while the PC is placed in a separate data VLAN. The link between the phone and the switch operates as the trunk, carrying both voice and data VLAN traffic over a single cable. VLAN hopping is a network attack in which a malicious actor gains unauthorized access to traffic on VLANs that they shouldn't be able to reach. To defend against this, implement the following best practices. Disable unused ports and assign them to an unused isolated VLAN. Change the native VLAN on trunk ports to a non-default unused VLAN to throw out double tagging exploits. Set access ports to access mode, preventing them from negotiating trunk links. Use VLAN access control lists to control inter-VLAN communications at the switch level. Enable port security to limit the number of MAC addresses per port and block rogue devices. Implement private VLANs for tighter isolation between hosts within the same VLAN. Disable dynamic trunking protocol to prevent unauthorized trunk negotiation. Deploy 802.1x authentication and authorization to validate device and user access at the port level. Continuously monitor and audit VLAN configurations to detect misconfigurations or suspicious behavior. And keep switch firmware and patches up to date to close all known vulnerabilities. An access control list, or ACL, is a set of filtering rules applied to switch ports or interfaces that determine whether specific network traffic is permitted or denied. By evaluating characteristics such as IP addresses, MAC addresses, protocols, or port numbers, ACLs act as gatekeepers, enhancing security and controlling traffic flow across network segments. ACLs can operate at different layers at the OSI model. Layer 2, data link, filters based on MAC addresses. Layer 3, network, filters based on IP addresses and higher layer protocols. ACLs are typically applied to ingress or incoming or egress outgoing traffic on interfaces. Types of ACLs include standard ACLs where filter traffic using only the source IP address. Simpler and less granular, often applied closer to the destination. Extended ACLs provide detailed filtering using source or destination IPs, protocols, and port numbers. It is applied near the traffic origin for precise control. Access control lists are evaluated sequentially. A switch processes each rule in order, and the first match wins. Once a packet matches a rule, that action, permit or deny, is applied and no further rules are checked. Common use cases for switch ACLs include device isolation within a VLAN, where it applies Layer 2 MAC-based ACLs to restrict communications between devices on the same VLAN, which is useful for guest or IoT segregation. Server access control, where use Layer 3 IP-based ACLs to restrict which IP ranges can reach critical servers, which is helpful for segmenting production, dev, and user environments. Traffic filtering that blocks specific types of traffic based on protocol or port numbers. For example, denying FTP or Telnet access while allowing SSH. Key design considerations would be placement, where you apply ACL strategically, inbound or outbound, depending on where you want filtering to occur. Rule order, since ACLs are evaluated top-down, rule order determines effectiveness. Place more specific rules higher and end with the general permit deny. In performance impact, where complex or poorly designed ACLs can burden switch resources. Keep rules streamlined and efficient. Here's a scenario. You have a small network with the following VLANs. VLAN 10, which is your management, VLAN 20, which is used for users, and VLAN 30 is for guests. Your goals: only allow administrators from the management VLAN to access the switches IP 192.168.10.1. Block guests from accessing any internal servers in VLAN 20, and allow users in VLAN 20 to access the internet, but not the management VLAN. Standard ACL examples would be, let's say you only want to allow access to the switch management IPs from a specific device in VLAN 10. Access list 10 permit 192.168.10.100. Interface VLAN 10. IP access group 10 in. The standard ACL only filters based on the source IP. Extended ACL examples now. Let's block all devices of VLAN 30, the guest, from reaching servers in the VLAN 20. Access -list 110 deny IP 192.168.30.0 000.255 192.168.20.0 000.255. Access List 110, Permit IP any, Interface VLAN 30, IP Access Group 110 in. This extended ACL uses both source and destination IP ranges and allows all other traffic to flow. In ACL and firewall rules, 0.0.0.255 is typically used as a wildcard mask. It specifies which bits of an IP address should be examined when the firewall rule is applied. A wildcard mask is essentially the inverse of a subnet mask. The subnet mask has a 1 in a bit position, meaning the corresponding bit and the IP address must match. The wildcard mask will have a 0 in that position. Conversely, if a subnet mask has a 0 in a bit position, indicating it can vary, the wildcard mask will have a 1 in that position. In this case, 0.0.0.255, when converting a binary, has zeros in the first 3 octets and 1s in the last octet. This means that the firewall rule will only consider the first octets of the IP address, allowing the last octet to vary. When used with an IP address like 192.168.1.0, the wildcard mask 0.0.0.255 specifies a range of IP addresses from 192.168.1.0 to 192.168.1.255. The firewall will apply the rule to any IP address within this range. To specify a single IP address using a wildcard mask, you would use 0.0.0.0. This mask indicates that all 32 bits of the IP address must match exactly. Therefore, a wildcard mask of 0.0.0.0 paired with an IP address will match only that specific IP address. To match any and all IP addresses, the wildcard mask you would use is 255.255.255.255. This wildcard mask essentially tells the device to ignore all bits in the IP address, effectively matching any possible IP address. Now, a bonus access control rule would be blocking users from accessing management VLAN, which prevents VLAN 20 users from reaching VLAN 10, except perhaps for DNS or specific ports. Access List 120, deny IP 192.168.20.0, 0.0.0.255, 192.168.10.0, 0.0.0.255. Access List 120, Permit IP any, Interface VLAN 20, and IP Access Group 120 in. This extended ACL uses both source and destination IP ranges and allows all other traffic to flow. Port mirroring, also known as Switch Port Analyzer or SPAN in Cisco environments, is a switch feature that duplicates network traffic from selected source ports or VLANs and forwards it to a designated destination port for analysis. This capability is widely used for troubleshooting and diagnosing network issues where you can capture real-life time traffic from a device or port to diagnose, performance analysis, send a copy of traffic to the intrusion detection or prevention systems to inspect packets for threats, and record traffic for audits or investigate security incidents. Best practices considerations include performance impact, where mirroring high volumes of traffic can tax the switch's CPU and memory, which means that you should limit usage on production networks. Dedicated monitoring port, where uses a dedicated destination port to prevent mirrored traffic from interfering with standard operations. Secure handling, which ensures only authorized personnel can access mirrored traffic to detect sensitive data and maintain compliance. And load awareness, where not all switches handle port mirroring efficiently under heavy traffic, where you would need to check platform capabilities. Question: you connect multiple unmanaged Layer 2 switches to create a large network for a new office with multiple connections between the switches. Now the network is experiencing an extreme amount of latency. Which of the following is most likely occurring? Answer: broadcast storm. Question: to comply with industry regulations, all communications destined to a secure server should be logged and archived on a storage device. Which the following will fulfill this requirement? Answer: port mirroring. Question: you install a new data and VoIP network. Users are experiencing poor call quality when making calls. What should you do to increase VoIP performance? Answer: configure a voice VLAN. Question: you want to monitor and provide traffic segmentation across the network, and you want to assign each department a specific identifier. Which of the following would you use? Answer: VLAN tagging. Question: a company's VoIP phone connection is cutting in and out. Which of the following should be configured to resolve this issue? Answer: 802.1q tagging. Question: remove an old PC from the network and replace it with a new PC that is unable to connect to the network. Which of the following is most likely the cause of the issue? Answer: port security. Question: what would you use to mitigate unauthorized physical connectivity on the network? Answer: port security. Question: which of the following is the IEE link cost for fast Ethernet interface and STP calculations? Answer: 19. Question: which of the following is used to elect an STP route? Answer: a bridge ID. Question: you need to increase bandwidth to a server which has multiple gigabit ports. Which of the following can be used to accomplish this without replacing hardware? Answer: LACP. Question: which of the following are reasons to enable jumbo frames? Choose two answers. Answers: increase payload size and to reduce CPU overhead. Question: which of the following network devices can perform routing between VLANs? Answer: Layer 3 switch. For more information, visit these sites. In summary, port security is the process of restricting access to a network by limiting which devices can connect to the network and how they connect. When you connect switches, often you want redundant paths. However, depending on how the switches are connected together, the paths can form a loop, which can cause denial of service with broadcast storms, network congestion, and other issues that can lead to network outages or degraded performance. The Spanning Tree Protocol, or STP, is a network protocol used to prevent loops in Ethernet networks by creating a loop-free topology. A virtual local area network, or VLAN, is a logical grouping of network devices that appear to be on the same LAN, even though they're physically located on different segments of a larger network. IEEE 802.1q is a networking standard that defines VLAN tagging and trunking. VLAN trunking connected switches together and allows multiple VLANs in a single link. VLAN tagging adds a 4-byte tag to Ethernet frames to identify the VLAN to which the frame belongs. Link Aggregation Control Protocol, or LACP, is a data link layer protocol that allows network devices to bundle multiple physical ports into a single logical channel called a link aggregation group, or LAG. Thank you for watching this video. The next video will be Networking Implementations, Part 4, Switch Architecture. If you like this video, click the like button, and if you have not already, subscribe to the Pat Has Your Back channel. Thank you.